Okay, this is section 4.5 for MAC 1105, last section of the book. Yippee! So we're going to be looking at exponential growth models in this particular section. And in the very first one, you see an example of one of those growth models. It's got the exponent up here, which is why it's called exponential growth. This describes what's called the initial amount. What you see over here is the final amount that it grows to. T is for years. This is called the growth rate. I mean, sometimes some of the things are declining and you'll see a negative rate there, but for the most part, these are growth rates. Then it says, this describes the population of a country in millions T years after 2003. Use the model of the population. Use the model to determine the population of the country in 2003. So since T stands for how many years have happened since 2003, and yet they're telling you to evaluate at 2003, that means they want you to use this model at 0 years because they haven't allowed any time to transpire. So it would be 937.5. This model was determined in the year 2003. 0.005. And they're already asking you to figure out how many people are in the population in 2003, so no time has transpired. So literally what they're asking you in this problem is the initial population, because anything to a 0 power is 1, and then 1 times the original population or the initial population is the answer. So the answer for this is 937.5. This model was designed in millions, so this answer is in millions. 937.5 million. So that you can just fill that in with this. 937.5. They've already provided the word millions for you. You don't need to put a bunch of zeros on there if they've typed in that word. Then it says the exponential models over to the right describe the population of country A in millions, T years after 2006. Which country has the greatest growth rate? And by what percentage is the population of that country growing? So the growth rate, again, is this multiplier, the coefficient of T. So that's a negative one. That is definitely not even in the running for what is the greatest growth rate. So we'll forget about that one. But out of these three, the one that's the largest is the 0.02. That's bigger than 0.01 and definitely bigger than 0.00. So this would be the biggest one. So that is country number 3. And then it says the population of that country is increasing by what percentage? Well, this is a decimal. So if you were going to turn that into a percentage, it would be 0.024, but then you move it 2 places if you want it to be a percentage. So that would be 2.4%. Okay, number 4, the exponential model. Initial population of 832. Again, this is in millions, so that's 832 million. Of a country, T years after the year 2003. Use the model to determine when the population, so you're solving for T, when the population of the country will be 1,282 million. They want to know when this will be the final amount. So I'm going to work some of these out. Let's see. I don't know if I can fit this in here, but I think I'll do it on paper. Okay, so doing this problem here. This would be number 4. So I'm following this model right here. They want to know when the final amount is 1,282 million. The initial population was 832 million. It's growing at a rate of 0.018. You can write the 0 there, but not really necessary. And they want you to solve this for t. That's why the question is when. So the first thing you're going to want to do is get rid of this coefficient. Just let it dissolve right into the 1282. You can get that on your, so you have like a nice cleaner expression on this side. So you're going to go in here in your calculator and do 1282 divided by 832. And I got 1 point, I like to hold on to 4 or 5 numbers after the decimal just for better accuracy, 087. Better accuracy on your final answer. Okay, and then here, all you have is 0.018. We saw some problems like this even in the last section when they're the way that you can solve an exponential equation, knock this variable out of the exponential position, is by taking the log of both sides. But what would work particularly well in this problem is natural log, because the equation has an e in it. And that's because the base of a natural log matches that augment. So on this side, on the right side, you can use the inverse property, where this takes this out, takes the word log with it. That's from section 4.3. That property was introduced, where the augment matches the base, takes all of that out, and down comes the entire power. Then this you can just put in your calculator. That's going to be ln of 1.54087. Let me move this down a little bit. Cramming it right in there. So I have 0.018t on the right. ln of 1.54 is 0.432. 35. And then you're almost into the answer. Just divide that coefficient right off of the t. That's going to be that divided by 0.018. And you get 24.019. Let's see what they tell you to round it to. Okay, round to the nearest year as needed. So t is approximately 24 years. Okay, moving on to number 5. Number 5 has a couple of different questions, so let's look at the different things that are being asked there. They give you this formula. Again, the A with the 0 hanging off of it, that is the initial population or the initial amount. And the A that's on the left side is the final amount or the final population, in which t is the number of years after the year 2000. So they're telling you that this model was developed in the year 2000, and now in the year 2040, it's projected that the population will grow to 9 million. Okay, so they're giving you a lot of information here. The final amount in the year 2040 will be this 9 million. The initial amount is what it started off as, 5.76 million. And it takes 40 years for that to happen, for it to go from 5.76 million all the way to 9 million. 40 years have transpired. So that's t is equal to 40. And they're giving you all this information so that you can find k. Because you have this, you have this, you have the t. The only thing you don't have, because e is just a number, the only thing you don't have is the k value. So by finding k, you'll be able to go on and solve part B. Okay, so part A, let's see if I can fit it in right here. This is the formula. Final amount is 9. Initial amount, this whole thing was developed in terms of millions, so you don't have to put a bunch of zeros on there. We don't have the k, but this is being multiplied by 40. 40 years have transpired, so 40 times k. I'll put the 40 in front of the k just because that's where we write coefficients instead of writing them in the back. All right, so you're going to solve this just like I solved number 3 or number 4. I divided this coefficient right off of the power expression, which is this e to the 40k, so that it dissolves right into the 9. So it goes away on the left. Then I can go to my calculator and do 9 divided by 5.76. And that's 1.5625. And then over here I have e to the 40k. And then in order to knock that 40k right out of the air, I'm going to take the ln of both sides, ln of 1.5625, and I'm also going to take the ln of e to the 40k. I'm going to have to do the rest of these on paper. I'm running out of real estate here. Okay, so on this side, an ln has a base of e, so this cancels with this, takes out the ln, and down comes the exponent. On this side, you're going to do it in the calculator. This is just like number 4, what I was doing in number 4. So ln of 1.5625 is 0.44. $629. And then just divide that 40 off, and you'll have the growth rate. Okay, so I got as the growth rate 0.0111 or 11. I'm going to keep that many numbers. Okay, so that was my growth rate. I kept 5 numbers. Okay, so then let's see. So the k value, and let's see if they wanted you to round to a certain number. I don't think they didn't give her anything in part A. So this is the answer. And then this is all the work. Part B. By which year, now that you don't know what t is, by which year, so instead of knowing this is 40 years down the road, now they're asking you how far into the future will the population grow to 13 million. So again, let's use this formula that I have right here to get this set up. So it will be 13 is the final population. The initial population, as it says in the directions, is 5.76, and then it's e to the rate, which we just found, e to the k times t, 0.01116 with a little t right there. And then if you continue solving that, I'll do that right here. So this is 5 point B. So there was a 13 on the left, 5.76 on the right with an e to the 0.01116 with a t next to it. So just like the previous two problems, I'm going to get rid of this coefficient first. Divide by 5.7 on both sides so that I clean up my exponential expression and get it ready for me to take the natural log on both sides. So I have the point 0.1116t, and then over here 13 divided by 5.7 is 2.28070. Okay, then at that point, you can jump into taking the ln. So you see that this is a major skill in this section. And this taking the ln of both sides is a way to deal with solving for a variable that's in the exponential position. This is one of the log properties that allows you to bring it down out of the air. So 2.28070, we're going to put this in the calculator. The reason that this power comes out of the air is because of the inverse property that we learned 2 sections ago. When the base matches the augment, these cancel, take the word log with it, and down comes the power. That's the inverse property. So in essence, you are bringing that exponent out of the exponential position and down into a position where you can solve it. You're going to get this from your calculator. Okay, so this is ln of 2.28070. That's equal to 0.82448. So almost there. 13 divided by, I just want to check something real quick. Okay, so last step, you're going to divide this coefficient right off of the t, likewise on the other side. That's going to cancel, and you're going to have t is equal to, and we'll round to whatever they said. So it's 0.82448 on the top, divided by 0.01116, and that is 73.8, approximately 74 years. Let's see what they want in this problem. So in part B, it says by which year? I guess they want it in the, by which year will the pot, okay, so this is what we got for the answer. This is going to happen approximately 74 years later, where this is going to go to 13 million. So we have figured that out, but look at the way the question's asked. By what year will this happen? We just know how many years it's going to take. But the model that you're using for this problem, it begins in the year 2000. And you're adding 74 years to that. That's when it's finally going to reach 13 million. So 2074. Okay, we got a t value of 74, and then we added it to where this model began. It began in the year 2000. For this, we had gotten the 0.01116. I'd put it up there though. And then this is all the work for part B. Okay, moving on. Moving on to part 6. Okay, complete the table shown to the right. Okay, 2000 projected population. This is the growth rate. The projected 2037 population. So this started in the year 2007. Now we're talking 30 years into the future. So projected population in millions at that time. Okay, so we're going to use this formula. Final amount is equal to the initial amount, and then it's E. The rate of growth goes right here. So it's just the exponential growth model times the number of years. Okay, so if it was 83.9 million, these problems are very repetitive, and then we want to know what the projected population is in millions, so we're looking for this. We have no number for this, and then it's times E to the 0.0188, and this is happening 30 years down the road. So 30 years have transpired. So we'll put that in for T, and then we're going to put all of this into the calculator. Okay, so that is, I'm going to go stick all of that right into the calculator. E raised to 0.0188 times 30 times 83.9. Or you can just put it straight in the way you see it. And I got, round to one decimal place, I got 147.5, and that's in millions. So it started off in the year 2007 at 83.9 million, and it has grown to 147.5 million. But they already provided the word million for you, so you just put the 147